I already talked about volcanic rocks, volcanoes, and volcanic landscapes. Those are amazing examples of igneous rocks that have crystallized on the Earth's surface and created unique landforms and landscapes. But igneous rocks also form at depth, creating rocks such as granite. These deep-formed igneous rocks are called intrusive igneous rocks because they intrude deep into the Earth when they're forming. They're also called plutonic rocks. These intrusive igneous rocks have very different characteristics from the extrusive volcanic igneous rocks that we discussed before. And because it takes a long time to exhume or expose those intrusive rocks, when they do finally appear, the landforms and the landscapes are also very different from the volcanics. What they have in common is that all igneous rocks are crystallized from a liquid. That always amazes me. Geologic processes generate liquid rock. How does that happen? Well, the heat, of course, comes from the interior of the Earth. Much of that interior heat was generated during the formation of the planet. But the decay of radioactive elements generates heat as well. The deep interior of the Earth at the core is almost 6,000 degrees Celsius. That's more than 3 times the surface melting point of iron. And it's hot enough to maintain a liquid outer core even at these depths. By the time that heat reaches the upper mantle, it is dissipated to about 2,000 degrees Celsius. This variation in temperature with depth is called the geothermal gradient. If you start from the Earth's surface, you gain about 3 degrees Celsius with every 100 meters of depth. But the temperature needed to reach melting point increases for rocks that are under greater pressure deeper inside the Earth. Think about it. The molecules of liquid usually take more space than a solid, so expanding to a bigger size under greater pressure takes even more energy for melt to occur at depth. In addition, the presence or absence of water will also influence the melting temperature of a rock. The result is that magmas are generated in varying conditions and settings. This variation in magma contributes to the wide variety of igneous rocks. Once a magma is generated, it will start migrating upward. If it makes it all the way to the surface, then it becomes a volcanic or extrusive rock. But that usually doesn't happen. In fact, given the weight of overlying rock and the influence of colder temperatures of the surrounding near-surface material, you can understand why volcanoes only form in specific geologic settings favorable to magma migration. So it makes sense that overwhelmingly the world's igneous rocks are intrusive. So with intrusive igneous rocks, you get magmas crystallizing at depth. Because deeper rocks are always hotter rocks, and because overlying rocks keep the magma insulated, magmas at depth will cool slowly. When this cooling happens, individual crystals form, and because they are still in contact with the magma, the crystals will continue to grow. As long as the particular mineral crystal is stable at the temperature and pressure and remains in contact with the magma, that crystal will keep growing. This is, of course, the origin of many spectacular mineral specimens that you see in books or museums. It's also the principle behind those kits that enable kids to grow sugar crystals on a string. As long as you keep the string immersed in sugar water, sugar crystals can get larger and larger and larger. It's an interesting process. This is why igneous rock crystal size, also known as igneous rock texture, is one of the fundamental components of igneous rock classification. Igneous rock texture, mineral grain size, divides the 2 main groups of igneous rocks. This granite, as you know, is an igneous rock with a coarse texture. That is, you can see and probably identify the minerals. This is called a phaneritic igneous rock. The magma cooled slowly, the crystals grew, and eventually an intrusive igneous rock body was formed. This is a rhyolite. It's a volcanic rock which cooled very quickly. The minerals didn't have time to grow. These are said to have fine-grained texture and are called aphanitic, igneous rocks, from the Greek meaning not visible. The chemistry of the magmas that yielded these coarse and smooth-textured rocks was essentially the same. Some igneous rocks have elements of both textures. This is a porphyry, and again, the chemistry is about the same as that of granite and rhyolite. The porphyry started out cooling slowly at depth, like a granite, forming large, coarse-grained crystals, which are called phenocrysts. This process, however, was interrupted and the magma was extruded. Then fine-grained rhyolite formed, contributing to what's called the ground mass. Porphyry is an interesting rock, and it was highly valued in ancient times, both as an architectural stone and for statues. The amazing porphyry basin now housed at the Vatican is a wonderful example. In fact, throughout Egypt, Greece, and Italy, you find porphyry used for brickwork, for walls, and for buildings. Most of it came from a single mine in eastern Egypt. The word porphyry comes from the Greek word for purple. Here's an example. Most Greek and Italian porphyry that's used as a dimension stone is a red and brown rock. The red color is from iron in the volcanic ground mass. The white or lighter colored crystals are quartz or feldspar. Porphyry was valued both for its hardness and for its unique color, purple being the color of royalty. Porphyry's hardness makes it difficult to shape, but imperial Romans had steel cutting tools, knowledge later lost in the Middle Ages. So imperial Romans carved togas, busts, and other statues in porphyry for especially important people. The Emperor Constantine erected an enormous column of round porphyry blocks to announce the empire's new capital in Constantinople. The mother and daughter of Emperor Constantine each have an entire sarcophagus carved in porphyry, now displayed in the Vatican. Due to the mix of crystal sizes, porphyry is harder than granite. That makes porphyry attractive for construction of resistant surfaces. In Scandinavia, where cars have studded winter tires, the asphalt is more likely to be made of porphyry aggregate because it can withstand more wear from metal studs than, say, an asphalt that uses a granite-based aggregate. The other major way of subdividing igneous rocks is by mineral composition. Most igneous rocks are essentially comprised of 8 minerals. These are commonly divided into 2 groups, a light-colored group and a dark-colored group. As you know from the lecture on minerals, the 4 light-colored minerals are muscovite mica, quartz, plagioclase feldspar, and potassium feldspar. They were referred to as the felsic minerals. And for the generally darker minerals, we have biotite, olivine, pyroxene, and amphibole, which are referred to as mafic minerals. So because of the color differences of these minerals, a quick and dirty way to differentiate intrusive igneous rocks is what is called a color index. It is essentially the ratio of mafic minerals to felsic minerals. The index ranges from 0 for brightest white to 100 for darkest black. The light-colored granitic rocks range from 0 to 25%, while the dark-colored mafic rocks made under the ocean are anything from 45 to 85%. Ultramafic rocks, such as this peridotite, are 85 to 100%. Ultramafics are relatively rare on the Earth's surface. So that's it. Texture and color index are all you need to start to learn the different types of igneous rocks. Igneous rocks that are light-colored and coarse-grained are all informally called granites, and they are dominated by felsic minerals. Igneous rocks that are coarse-grained but darker colored are sometimes called trap rock, but a more precise term is gabbro, which is the coarse-grained version of basalt. In between the light colors of granite and the dark colors of gabbro, there is an intermediate colored coarse-grained igneous rock called diorite. Diorite has minerals from both the granite and the gabbro groups. Taken together, granite, diorite, and gabbro are the main intrusive igneous rocks you will encounter in the field. But here's the rub. In a building supply store, a stone showroom, or even at a rock quarry, all three are likely to be called granite by non-geologists. This, for example, is called black granite, but it's really a gabbro. For geologists, granites are a light-colored rock made up predominantly of light-colored minerals, two kinds of feldspar, quartz, and muscovite. And there should be fairly large mineral crystals in it, at least large enough to be able to identify with a hand lens. Anyone who has ever taken the time to really look at coarse-grained igneous rock tends to be impressed with the wide variety of types and colors. This variety is impressive whether in the field, at different locations, or when it's used as dimension stone, whether for countertops or other building features. On a regular basis, students and I will stop in at a dimension stone showroom. It's just amazing. The natural variety of colors and minerals of igneous rocks is mind-boggling. How does this happen? Why is there such a wide variety of igneous rocks when they're made up of 8 principal minerals? It's an interesting question. The mineralogy of an igneous rock is influenced by many things. The temperature at which the magma crystallized will influence the ratio of felsic to mafic minerals. But there are other ways to change the chemistry of the magma and ultimately the minerals in the rock. One of the ways you generate unique igneous rocks is to melt multiple rock types. Of course, rock types melt at different temperatures, so there are some limitations to the chemistries you can get. But if you start generating heat and there's a lot of different parent material available, you'll generate some interesting magmas. Another way is to have magmas mix. If there's a lot of heat at depth, multiple magmas will be generated. It's possible that during magma migration, mixing occurs. Mixing is common, especially in big intrusive bodies of at least 100 square kilometers, and they're called batholiths. The formation of a batholith occurs in multiple stages. Over time, different magmas form at depth and will rise to be added to the overall body. Teachers often use a lava lamp as a model for batholiths, where the rising blobs meet at the top of the lava lamp and meld together to make a single large blob. That's a batholith. If a new magma is injected into the batholith and portions of it still haven't crystallized, that is, there's still liquid in the batholith, the magmas might mix. But it depends on whether the two magmas can actually blend together and form a new composition magma. Another way different magmas form is by the addition and assimilation of overlying or surrounding rock. The injection of magma into solid rock will many times destabilize that rock. Blocks of what is referred to as country rock will break off and melt inside the magma. This results in a new chemistry. The last way I'll mention that different magmas form is called fractional crystallization. If a magma remains in a liquid for a long time, minerals will crystallize. And because of mineral density, they will settle out, just like a sediment settling out of the ocean. The result of the removal of the mineral is an alteration of the changing composition of the magma. As a result, As the magma changes, the igneous rock that subsequently forms will also change. This is a process you may have actually observed. If you leave honey in a cabinet for a long time, and you can do that because honey resists spoilage, you may notice the crystals have formed and settled to the bottom. Those are sugar crystals. So think about it. The honey was sitting there, a little bit of water probably evaporated, and you get supersaturation of sugar. Crystallization occurs. Those crystals, as they settle to the bottom, are removing sugar from the honey. As a result, the composition of the honey is changed. In theory, if you let the sugar in the honey continue to crystallize out layer upon layer, you would observe a change in the chemistry of those crystals in each layer. That happens in fractionally crystallized magma, and the result is called layered intrusions. The result of all these magma formation processes is that you sometimes end up with igneous bodies that can be made up of just one type of mineral. This is Labrador Blue, and it is made up almost entirely of calcium feldspar. It's also called blue granite. Blue granite was used on the edifice of the Chrysler Building. So when you think about it, there's an abundance of magmas that can be generated in a number of different ways. The important thing to remember, though, when you're doing fieldwork, the identification of intrusive igneous rocks is pretty straightforward. I mean, if it's a large-grained and light-colored igneous rock, call it granite. So where can you see a granite? In North America, granites are exposed in the Appalachian Mountains, in the old rocks of the Canadian Shield, and along the relatively new batholiths near the Pacific. Besides batholiths, there are various smaller types of intrusive igneous bodies. These form in various geometries that are the result of the influence of the rocks they have been intruded into. For example, sills are sheet-like intrusive bodies, which form parallel to bedding planes in sedimentary rock. Across from New York City, the Palisades Sill on the cliffs of the west side of the Hudson River are a great example. Unlike the parallel patterns of sills, dikes are transverse patterns that cut through sedimentary rocks. A number of dikes together are called a swarm. One famous swarm of dikes is Shiprock in New Mexico. Sometimes during the formation of a volcano, swarms of dikes form in a radial pattern associated with the volcano's cone. Another reason to visit batholiths of granitic rock is that the resulting landforms are interesting as the geology of the rock itself. Frequently, granitic bodies are more resistant to weathering than the rock it was intruded into. The igneous body is eroded at a slower rate than the rock around it, and you create an upland that most people call a mountain. Spectacular examples include Stone Mountain, Georgia, the Black Hills of South Dakota and Wyoming, and parts of the Sawtooth Mountains in Idaho. Of course, what's totally cool is that 6 to 12 miles of overlying rock were first removed through erosional processes. Building a mountain by removing that much material is just crazy. In other cases, granitic rocks can be weaker than the surrounding rock. Sometimes planes of weakness are created at depth by tectonic forces that will result in extensive fracture patterns in the granite. Depending on the scale and the extent of the fractures, both weathering and erosional processes can exploit and enlarge those fractures. A classic example of erosional processes exploiting a fracture is Half Dome in Yosemite. Essentially, half a mountain has been sheared off due to glacial erosion and a number of other processes. There are also landforms that are the direct result of the removal of overlying material from an igneous body that was formed at both high temperatures and high pressures. Remember, intrusive igneous bodies form up to 6 to 12 miles beneath the land surface. So when minerals form in magma, they form under high pressures that are generated by the miles of overburden at temperatures over 1,000 degrees Celsius. Think about what that means when you bring that rock to the Earth's surface. those mineral crystals are going to be unstable. In other words, they will begin to break down. A feature that is frequently found in granite landscapes is an exfoliation dome. So let's go back to Half Dome. On the opposite side of the cliff, slabs of granite appear like an onion skin on the top and the sides of the dome. These slabs form as a result of pressure release or unloading of overlying material. As pressure is relieved, individual crystals in the igneous rock expand. The rock was once buried under 10 miles of rock, and now the only pressure is just atmospheric pressure. The result is the process called exfoliation. Now, exfoliation might sound like a gentle process that happens to your skin, but we know now it's more like an explosive decompression. Literally, the minerals expand and the rock cracks, and the debris will eventually fall off the top of that granite mountain. In 2015, what geologists mean by exfoliation was filmed for the first time. After visitors had described weird activity on a granite dome near Twain Harte Lake in Northern California, geologists went to check it out. As the camera is scanning the surface, you will hear a popping sound and see dust emitted as a slab of rock is exfoliated. The surface of the rock is literally being shed by the expansion of minerals. This is exciting stuff. Although this was the first time the process of exfoliation was filmed on the land's surface, a related process called rock bursts, the explosion of rock material due to the unloading of material above it, are well known in mining. Rock bursts in mines occur regularly. They can be quite dangerous, especially during the first couple years after a mine is dug. It's almost like shrapnel coming from the roof of the tunnel. Exfoliation is a significant enough geologic process to generate substantial volumes of debris at the base of a granite dome. Note, granite seems to be the only plutonic rock that does this on a regular basis. So if you see exfoliation, then you're looking at a dome made of granite. One more interesting thing about the breakdown of granite is the process of grussification. If you've ever broken up a slab of granite or maybe picked up a scrap from somewhere, you may have been surprised to find that it breaks apart pretty easily, given that it's a fairly resistant rock. Granite breaks apart because the minerals grow into one another during crystallization in an interlocking pattern. But there's very little holding them together. So when stressed, the minerals just break apart. Let me show you. This is also what happens in nature. Over time, the granite weathers and breaks apart into coarse-grained fragments called gruss, which accumulate alongside of the rock. This accumulation of gruss is what is called grussification. If you happen to find a granite or a gabbro boulder exposed in a gravel pit, under the right conditions, the weight of the surrounding material will keep the boulder together as it is grussified. My students call these ghost boulders because you can take a shovel and cut right through them. Let me show you. I should be able to cut this with a knife. It's an interesting feature. Let's turn to the economic uses of intrusive rocks. Intrusive igneous rocks are important for a number of economic reasons. Some of the world's most valuable ore deposits and mineral resources are associated with intrusive igneous rocks. The origin of these valuable commodities is the result of both the right magma chemistry and the way water interacts with the magma. There are several ways mineralization can occur. Remember fractional crystallization? As magma cools, minerals will settle out, and the density of the minerals crystallizing will influence the settling process. Under very special conditions, you can get the concentration of important metals from the fractionalization process, such as chromite, magnetite, platinum metals, and vanadium minerals. Important examples of deposits created by fractional crystallization include the Stillwater Complex in Montana and Red Mountain in Alaska. If fractional crystallization continues for a period of time, you can imagine the magma chemistry will continue to evolve as minerals are removed from the mix. In the final stages of magma crystallization, what remains are silicate minerals and gases. The gaseous phase will be dominated by sulfur. If you've ever been to an igneous hot spring or a volcano, the smell of sulfur predominates. It turns out that many metallic elements will bond with sulfur and be emplaced as metallic ores. Although metallic elements make up a small percentage of the igneous body, by the late stages of magma crystallization, the metals are concentrated. In late phases of igneous body formation, there's not much left in the magma. The addition of hot water to the system results in what are called hydrothermal ore formations. Sulfur and metal dissolve in hot water, and as the water migrates away from the magma through fractures, there are changes in pressure and temperature that will cause the metals to precipitate as sulfide minerals. These are frequently the vein deposits or lodes that you might hear miners talking about. The large gold and silver deposits in Nevada form as vein lodes, as do some lead zinc deposits in the Midwest. You can also get mineral deposits in small veins near the top of a magma chamber. These deposits tend to be both smaller and widely scattered, so they are referred to as disseminated ores. For copper, the misleading term porphyry copper is applied specifically to disseminated ores of copper. The distribution of small components makes it seem like it's porphyry. The Bingham Copper Mine in Utah, which is the third largest open pit mine in the world, has yielded $6 billion of copper and associated metal. One of the uses of igneous rock I mentioned earlier was the use of porphyry in asphalt. Where available, igneous rocks are frequently used in the construction of road surfaces. Asphalt, specifically stone mastic asphalt, is made up of 80% crushed rock. The rest of the mixture is bitumen, which is a petroleum product. Fibers can come from any kind of cellulose to help stabilize the mixture. Lastly, there's filler. Any fine particle can be used as filler, whether it's fly ash, which comes from burning coal, or any dust that results from the rock crushing process. But it's all the crushed rock, not the fine particles, that makes all the difference in the strength of the road surface. And that's where granite comes in. Granite is both strong and can be broken up into particles of uniform sizes. Most importantly is the angular nature of the crushed granite. When making stone mastic asphalt, the key is to pack the crushed stone tightly. When that happens, the angular grains come into contact with one another and essentially interlock. It's the high content of crushed stone that makes the road resist deformation and grooves. The formula for stone mastic asphalt was developed in Germany in the 1960s and is now widely used in Europe, Canada, Australia, and the US. It turns out there are lots of rock types that you can use for the crushed stone component of asphalt, but if granite is available, it's a good choice. Crushed stone is a multi-billion-dollar industry. Of course, by now, you're aware that the most comprehensive use of coarse-grained igneous rock like granite is in building construction. Granite is versatile enough for either interior or exterior design. You can use it for landscaping or for architectural detailing. Common uses of granite include staircases and flooring tiles, kitchen countertops, and even work countertops. Shower and bathtub surrounds and vanities in the bathroom, and there is a whole realm of monuments, tombstones, and sculptures. I'll warn you though, because of all the changes that can occur in a magma body, especially with a large batholith, there is a limited amount of igneous rock of one particular color. You now know that mineralogy of a magma is constantly evolving. That means if something happens to your granite countertop, for example, or you want to add additional counter space with more granite, you might not be able to match the original. I know this from experience. We put in the new kitchen and used the granite from a nearby quarry. Here's a remnant. After looking at our plans, the stonemason decided that he wanted to install it in one long piece without a seam. The problem was they weren't confident that such a long granite slab would be strong enough. I didn't know this at the time, but they drilled in a couple of stabilizing bars on the underside of the granite slab. It turns out those bars themselves caused the granite to crack. Bummer. They were really nice about it and immediately made a new replacement. But it was a different color. In the intervening 3 years after the original install, the quarry had progressed into a different mineralogy. Same granite source, just slightly different mineralogy and a different color. When they arrived with the new counter, I had found out they had anticipated the change and had already cut new granite for backsplashes and satellite sections of the counter. This happens all the time. It's a natural product. It's a beautiful product and well suited for interior design. But you have to remember that each piece is unique. I didn't mind the hassle. I totally love the countertop, and in a way, I like it more because it's so unique. Granite is abundant, strong, and distributed worldwide. The multiple ways that granite and other coarse-grained igneous rocks crystallize also means you'll get a wide variety of colors. If you're looking for a countertop to match a design scheme you're working on, there's a good chance you can find an igneous rock to match. Layered intrusions are really interesting. The accumulated layers imply that the magma has maintained consistent conditions over a substantial period of time. And remember, this was maybe 10 miles below the Earth's surface. What also happens is the crystals begin to behave like sedimentary particles. That is, the crystals form, they settle out, and they begin to accumulate. It's like snow crystallizing in the atmosphere and settling out, but 10 miles underground. Moreover, in some layered intrusions, it's been reported that the crystals have been transported during settling. The result is the formation of sedimentary structures like dunes or crossbeds, but deep below the surface. So that means there are currents in these big magma bodies, maybe even waves, miles below the Earth's surface. Geology is totally cool.